see. So the mastering physics due yesterday has many problems about the Gaussian law and also many problems about how to calculate the electric field. So I just pick up some problems I think is very important and to show the solution. And if you have any question, you can ask me. So I'm going to talk about the number 4 first, and also can answer the question and how to use the Gaussian law. And last class on Wednesday, we talked about the Gaussian law. That is, if we have a closed surface, any surface, okay, so any surface, no matter what is a box or sphere or cylinder, and if this closed surface include charges inside, positive charge, negative charge, or different value of charges, then these charges generate electric field. And this electric field go through the surface. So on the surface, you will have flux, electric flux. The electric flux we use psi or phi to represent, and depends on your preference. So here I use phi to represent the flux. The flux of the surface is equal to 4 pi k times the q. The q here is a total charge inside the closed sphere. Inside of the closed sphere. Closed surface. Okay, so if we have 3 charge, we have to sum the charge this way. Sum up all the charges inside the surface. Okay. And also, this is one equation we have to represent the flux. Because different people use different notation, someone like to use epsilon naught. And we know the two equations are equivalent. The electric field equal to K, the center charge over distance square, and the electric field could be written in the other way, 4 pi epsilon naught Q over R squared. These two equations are the same. And just because different people use different notation, and we have the relation K equal to 1 over 4 pi epsilon naught. Okay, so some people want to use epsilon naught to write the Gaussian law. So in this case, the phi could be written as a total charge inside the closed surface over the epsilon naught, or 4 pi k times the total charge. They are the same equation. Okay, so in this problem, they ask you to use epsilon naught to formulate your result. So this is the first one I want to emphasize. Then let's go back to the question. So what's the electric flux through surface A? Surface A is here. This is surface A. So this is a closed surface. So for the closed surface, we can use Gaussian law. The flux, total flux, is equal to the total charge inside the surface A over epsilon naught. Okay, then let's count how many charges are there in the surface A. There is 3q charge and 1q charge. So we sum up them, 3q plus q over epsilon naught. We don't count the charge outside the surface A. So we don't count the minus q or the minus 3q, because these two charges are on the outside of the surface A. So, and the result will be 4 times Q over epsilon. If you have any question, you can stop me. Then let's move to the surface B. Here, the surface B. Oh, this is better. Okay. For the surface B, it includes two charges. The two charges have different values, and the flux of surface B will be the total charge inside, that will be minus Q minus 3Q over epsilon naught. Okay, so we have minus 4Q over epsilon naught. Okay, then for the surface C is here. It includes two charges. They have the same value but different direction, or a different sign, not direction. So for the flux C, that will be equal to the Q plus minus Q over epsilon naught. So the total flux is 0. And you can think it in this way. For the positive charge, it generates electric fields and it goes outside. And for the negative charge, it generates the electric field, but it goes inside. And you see the inside electric field is equal to outside electric field. So in equal to out. So they cancel out. The total flux is 0. Okay. So this is for the surface C. And let's go to the surface D. Surface D, 3 charges, 3Q, Q, and minus Q. So the total is 3Q. The flux is 3Q over epsilon naught. Okay. And for the surface E include all the charges, and they have positive charge and negative charge, but the total is 0. Okay. So the total charge is 3Q, Q minus 3Q. That's 0. So the flux is 0. Okay, so for these questions, to use Gaussian's law, we have 2 steps. First one, we check if this is a closed surface or not. If this is not a closed surface, we can't use Gaussian's law. So closed surface, then second one, count the total value of charges inside of the closed surface. Okay. And we don't count the charges outside the surface. Okay, this is the trick to solve this kind of problem. Any question? If no, let's move to next problem, number 6. Number 6, we are going to calculate the electric flux through a non-closed surface. Okay, we have a cube. The cube dimension is 5 by 5 by 5. This is dimension. And what's the electric flux through the top surface of the cube? Top surface. So if we have a surface, we have a box, cube box, and there is a charge at the center. Okay, so that means everything is symmetrical at the center, and we have the value of charges of 17 nanocoulomb. And we are going to calculate the electric flux on the top surface. There are 6 surfaces on the cube. Surface on the cube. And each surface will contribute to the same flux because it's symmetrical. Okay, the symmetrical geometry, because of geometry, this geometry is symmetrical. So each surface has the same flux. If this is true, we can calculate the total flux. The total flux could get from the Gaussian Law. Then we use the total flux divided by the number of surfaces. That's a 6. For the total box, this is a closed surface. So the electrical flux inside this cube will be the charge inside, that's the 17 nanocoulomb over epsilon naught. Okay, this is the total flux and divide by 6. Okay. And the epsilon naught, I give you the value that will be 8.85 times 10 to the negative 12. Okay, so this is the solution for this problem. And let me move to next question. Number 7. For the number 7, we are going to talk about the conductor. Okay. The conductor actually is a little bit tricky. And so I'm going to introduce the conductor first, then talk about go back to this question. Here, for the conductor. Okay. For the conductor, suppose we have a box. This box is made by metal. For example, we have aluminum or steel or brass. Doesn't matter. It's a metal. And there is external electric field generated by the cable or by the generator, but doesn't matter. We just generate an electric field outside of this box. And this box is made by metal. So that means there is free electrons inside the box. So this negative charge and the positive charge will be polarized by the electric field. So in this case, at the beginning, if there's no electric field, the positive charge and the negative charge are distributed randomly inside the box. And the number of positive charge is equal to the number of negative charge. So the box is neutral. But after we generate the electric field outside the box, the external electric field is going to push these charges move at a different direction. So the positive charge is going to move to the right. And the negative charge is going to move to the left. So eventually, at a steady state, the electric field on the outside is going to move the positive charge and the negative charge to the different sides. And you will see the polarized charge is going to generate an internal electric field, and the direction is on the opposite direction. So you see, the external electric field, external is to the rightward, and the internal electric field generated by the polarized charge is going to left. So at the steady state, the external electric field is going to equal to the internal electric field. And the direction is on the different way. So the direction are opposite, then eventually these two electric fields cancel out. So inside of the box, the total electric field is equal to 0. So that means if we have a conductor and there is an external electric field, this electric field is going to driven or drive the electric charge inside the box, move to the edge, and at the steady state, the electric field inside the conductor is 0. And this process is very quick. We said at the steady state, E is equal to 0. And from the beginning to the steady state, this process is very quick. It takes a millisecond to reach the steady state. So that means if we want to protect somebody from the lightning, we can make a metal shield. For example, if you are on the outside and there's a heavy raining and a big lightning, okay, and you stand here, to protect yourself, you need to find a metal shield. You need to put a shield made by metal. And the lightning is going to generate electric field, but the shield has a free charge. Then if they have free charge, if there's a free charge, then we will have, let me see, the positive charge reach on the right side as a negative charge reach on the left side. So eventually, the generated charges is going to cancel out the lightning electric field. So make you at the 0 electric field space. So you're safe when you stand in the metal shield. We call this electric shield. So actually, if you have a cell phone and you put the cell phone in a metal box, the cell phone will lose the electric signal. The signal actually is electric magnetic field, and they just translate in the space. But if you put the cell phone into a metal box, the metal box is going to screening the cell phone, and you will not receive any signal. And the same case, if you live in a very big building, and the building is made by metal, and you will see a lot of steel or copper, then inside the building, it's very hard to receive signal because the electrical signal is screening by the building. And in this case, if you want to get a signal, we have to set up some routers or the electric field generator inside the building, then make sure the people inside the building can receive the signal. Okay, so this is the conductor. And I have a video to show how people use electric shield to protect themselves. Okay. And there is a video I take from the YouTube. Mm. See, okay. So here you see, there is a person standing in a metal cage. This cage is made by metal, and on the left side there is an electric generator, and this generator is going to generate a high voltage electric field, and you will see a lightning attack this cage. But this guy is protected by this cage, so he will be safe. I show this video for you, and he's doing the performance, and you see. So where does it stop? Okay, we can. Okay, you see, the generator creates a lightning, and the cage um, is doing the shouting and screaming this man, and you can see it again. This is not a Hollywood movie. It's a real lightning, and this generator can generate a very large and high voltage lightning, and this guy is protected by this cage. This cage is called threaded cage. So if you see somebody work on outside with an electric cable, they need to uh, wear some jacket to protect themselves. The jacket is made by metal. So I show some picture. Let me close this video. And here you see when these guys work outside and the electric cable needs the fix, but I think the company cannot shut down the electricity because there are many users using the electric cables at the same time, so they cannot turn off the electricity. So this guy have to work with the electricity on. So this guy need to wear a very special jacket. This jacket has a very metal um, uh, pieces inside the jacket. This jacket is very heavy. So they made by metal, and the metal is going to shield this guy and protect this guy. So the principle is easy. The metal is going to screening the electric fields from outside to protect this guy. Okay, this is the electric field screening or the shield I'm going to talk today. Then let me go back to the question. So stop this sharing. Hold on, give me a second. Okay, go back to the question. You see, there is a conductor, and we're going to calculate the electric field inside the conductor. Top. Which one is correct? See, first one, the field inside the conductor. If the field inside the conductor, the electric field has the same direction as original external field. This is not correct because inside the conductor, the electric field is equal to 0. If this is equal to 0, we don't talk about the direction. So this is not correct. This is also not correct. And this is not correct. So we only have this choice, and it's always 0. It's very important. And next question, what's the charge density inside the conductor? So how do we figure out this question? Inside the conductor, we know the electric field is equal to 0. So we can use Gaussian's law. Hold on. And we can use Gaussian's law and to sketch any closed surface inside the box anywhere. And each closed surface will give us a flux. The flux, equal to the electric field on the surface times the total surface area. And according to Gaussian law, we have this value equal to the charge enclosed the surface over the epsilon naught. Or you can use 4 pi k cube. Okay, then you will find that anywhere inside the conductor, the charge is equal to 0. So the flux equal to 0. And 0 over the total area of the surface is the electric field. So the electric field is equal to 0 anywhere inside the conductor, right? Because you see, this is 0 because inside the conductor this is 0, so the flux is 0. If the flux is 0, then there's no charge inside the surface. If there's no charge, then the charge density is 0. Okay, so this is the reason why we pick up 0. And next one, let's see. Next question, number 8. Now this one, I go to the number 12 or number 10. Number 10, okay. Let's going to use Gaussian's law to make this question seem easier. There is a non-conducting sphere. Okay, that's very important. This is a non-conducting sphere, and the radius is 2 centimeter, and the total charge is 1 millicoulomb, and it's uniform distributed through the volume. Okay, so the volume density is uniform. And at what distance measured from the center of the sphere does the electric field reach a value equal to half of its maximum? Okay, so the first question is, where is the maximum value? If we have a sphere and from the center to the outside, and we establish a coordinate, suppose this is x, or we use r. And the electric field is y-axis. How does the electric field distribute on the radial direction? Let's use the Gaussian's law to solve this problem. So hold on. If we want to calculate the electric field outside the radius here is capital R. Okay, R larger than the capital R. And we can sketch a closed sphere. Okay, we sketch a closed sphere, and this sphere has a radius, that's R, and we can calculate the flux. The flux is equal to the total surface area 4 pi small r squared times the electric field. Okay, then this will be equal to the charge inside the sketched surface. That will be Q over epsilon naught. Or you can use 4 pi k cube. Doesn't matter. Depends on your preference. Then you will get the electric field outside the sphere. That will be Q over 4 pi epsilon naught r squared. I just solved E. Solve the electric field, then you will find the electric field has a relation of 1 over r squared. It's proportional to the 1 over r squared. So outside of the sphere, the electric field, this is the radius of the sphere, outside of the electric field, outside the sphere, the relation of the E versus R is 1 over R squared. Right? It is 1 over R squared. Okay, this is electric field distribution outside the sphere. Then let's calculate the electric field inside the sphere. Inside the sphere, and we sketch a closed surface inside the sphere, and we write down the Gaussian law, the same thing, and will be the flux equal to 4 pi r. R is this one, r, 4 pi r squared. This is the surface area of the small circle, and times the electric field on this circle, and this will be equal to the charge over the epsilon. But be careful, the charge is not Q. Q is the total charge of the whole sphere. Whole sphere. Now, the sketched circle here is just a part of this sphere. It's not the all of the sphere. So the charge density is uniform, so we just use the volume to do the ratio, then we get the charge. The total charge is a Q, right? Total charge is a Q. Then the volume of the small circle is 4 pi over 3 small r cubed. Then over the total volume, that will be 4 pi over 3 capital R cubed. So the volume had a ratio, so the charge had the same ratio, right? So we can organize the equation. We have Q over small r cubed over epsilon naught capital R cubed. Okay. This is the tricky things, I think, when we do the electric field inside the sphere. Then you will use this equation to solve the E. Okay. So the E could be solved as capital Q R cube epsilon naught capital R cube over 4 pi R squared. 4 pi R squared. And you will see on the numerator, there is an R cube. On the denominator, there's an R squared. So eventually they canceled. We only have R1. Okay, so the electric field is proportional to the R. This is a linear relation. So inside of the sphere, the E versus R is linear line. So we can draw from here. Then we figure out the electric distribution all over the space. And if we ask you to calculate where the electric field has a value equal to half of maximum value, there are two positions. One is inside the sphere, the other is outside the sphere. And we use this relation, we can determine the 2 points and the 2 positions. Okay, this is the solution for this question. And I think this is very important. And we have the similar problem in the R exam. So you need to know how to sketch a sphere to calculate the electric field for the sphere. And this is for the mastering physics. And one more thing I'm going to talk about today is the electric potential. Electric potential. Okay, the electric potential actually is similar things as the gravitational potential energy. So here, let me give a short introduction. In the gravity, if we have a ball and the force and on the ground, force to the ground, then the balls will gain kinetic energy, right? The kinetic energy of this ball change is equal to the potential energy change. So the kinetic energy change equal to the change of potential energy. And the potential energy of this ball depends on the height this ball falls, right? Suppose the height is capital H, then we know the weight of the ball is mg. Then the potential energy is equal to mgh. Okay, this is the potential energy of the ball in the gravitational system or under the gravity. The same thing in the electric field. If the electric field is a uniform distribution and there is a positive charge and the charge is a Q, the value is a Q, and under the electric field, this charge is going to move and the speed increase. So it will gain some kinetic energy. Suppose the kinetic energy at the beginning is 0. Then the kinetic energy at the end, for example here, will be equal to the change of the potential energy. And now we want to find a way to define the electrical potential energy. The electric potential energy actually depends on how much work the electric field do on this charge. So we know the work done by the electric field is equal to the force times the distance, right? The force on the positive charge is the charge times the electric field. Then this times the distance. This is work and the electric field do on this charge. So we define this multiplication as the electric potential in this electric field. So we say the electric potential energy equal to the charge times the electric field times the distance. Okay, and we know the charge in this motion doesn't change. The charge is constant. Charge is a constant. So the change will be the E times L. So the E times L is the property that can reflect the space distribution of the electric field. So we call this combination as electric potential. So I use a new page. So we know the work or electric potential energy equal to the charge times the electric field times L, and we define E electric field times the distance as a new physical property. We call it electric potential. Electric potential. Okay. Oh. Cool. Electric potential. Electric potential. Okay. Cool. Get it. Ooh. It's annoying. Okay, anyway, electric potential. Okay, so if we know the electric field, we just need to times the distance, then we will get the potential. Or we use the potential divided by the distance, we will get the electric field. Okay, so if we ask you to calculate the electric potential energy, then we will have electric potential times the charge. Okay, this is a definition. Ooh. Okay, anyway, this is a definition. So if we have potential, then we can calculate the electric field. If we have the field, we can calculate the potential. Okay, so I think this is I'm going to talk about today. Then I will spend 10 minutes for you for the quiz. So now you can go to the quiz, go to the course site. I show you how to get the quiz. On the course site, can you see my screen?
Yeah.
Okay, good. So let me make this visible. Show. So under the section, you will see the quiz, the PDF, and you are supposed to submit your quiz on the top. So you will see there is a topic, upload your solution for today's quiz. So there is a submission link, and you take 10 minutes. You use 10 minutes to take this quiz. Then I give you 20 minutes to do the uploading. So save your time. And also, you can find the equation sheet on the course site. So this is what I'm working today. So if you finish, you can go. And if there's no more question, we will see you on Wednesday.